an Euler criterion, and Gauss come up with a nice description. Remember Fermat's little theorem? Who remembers how we proved Fermat's little theorem? Frobenius theorem was the second approach, which turns out to be more fruitful. Right, we multiply A through, right? A and 2A and 3A and 4A, and then it's a permutation, it turns out, right? So if you multiply all of them, it's kind of the same thing, but A is repeatedly multiplied with the number of multiplication A is p to the minus 1. So Gauss decided to use the same idea. Looking at the Euler's criterion, I'm looking at p minus 1 over 2. So I'm going to look at p minus 1 over 2 numbers, multiply all through A, right? And multiply with the same trick, the Fermat's little theorem, which Euler proved, I think. And the Gauss is using that idea. And that's what that mu is. Okay? So here's the description of mu. I want you to go ahead and write this one down. Gauss's lemma is pushing what Euler did a little bit further, that's all. All right, I'm using this notation because as a number theorist don't use this notation like 5 mod 3. They don't use that. They only use mod for congruence relation. But computer scientists, if they write it 5 mod 3, that represent 2, right? Remainder. But number theorists usually don't use that. So I came up with this notation. Least non-negative residue, mod n, I'm going to denote it like this, just for this Gauss lemma. It's a remainder, actually. Maybe I should have used REM instead of RES. Same thing. All right, mod is for congruence relation. This is a particular number we are assigning. What is that mu that Gauss came up with? And here's a description. L, throughout today's lecture, L is p minus 1 over 2, always. Half of the quadratic residue. I mean, that's the size of quadratic residue, right? And then you see the number in the Euler's criterion. That's motivation. So Gauss looked at 1 through L, right? 1 through L. And what Gauss doing is that he's going to multiply A to everywhere. So the book uses notation. I think it's a fine notation. AP. So AP is multiply A to the everything. Is A and 2A and 3A all the way up to LA. Make sense? Then if you multiply all of them, do you see A to the L coming in? If you multiply all this thing, that's the idea. But it's not as simple as the Fermat's little theorem. That's why it's a little bit, but it's not too complicated. So let's just go straight to what this mu is. What is the description of mu? In that P, 1 through half, the residue classes, if you multiply that by A, which is any of these, right? Its remainder is greater than L, right? So we looked at 1 through p minus 1, we split it in half, right? As we multiply by 2, and then find this remainder again, it may happen to land outside this half residue system. We'll see an example. How many of them will go outside the half residue system is that mu. And if you raise that to the -1, even and odd, he's claiming that that is the quadratic residue. So here's an example. So this is very silly exercise. It's about counting exercise. I already did the computation. I think this computation you can do absolutely on your own. Example 7. P is 19, right? And we are measuring this 11 mod 19. 11 quadratic residue or not. 1 or -1. That's what we're about to decide. Okay? And Gauss is suggesting look at half residue system, 1 through L. What is L here? It's 19. P minus 1 is 18, right? So L is half of it, is 9, right? So P is 1 through 9. And remaining 10 through 18 is the other half of them. Why are we looking at half of them? Because Euler's criterion is talking about half of them, so he chose that class. It actually doesn't matter which half you choose. It always has this property. That's quite amusing. But if you just choose the first half of them, then what do? We multiply by this A, which is 11 there, right? If you multiply 11, you can see the numbers get bigger, right? But I did the remainder in here. I wrote it down. So I've used a notation. Instead of number remainder, I did all that to the elements inside 11 times p and wrote down remainders in there. And your exercise number 2, right? Is that number 2? Is computing mu. That's your exercise. What is mu? This is 11 times p reduced mod p, right? Mod 19. How many of them inside there is outside the half register system? Right, by looking at them, what is the answer? 11 is over, right? 14, 9 is not. 17 is, right? 12, that's it. Right? 4 of them. Make sense? 4 of these things, after you multiply by that fixed element, went outside the half register system. Right? So, plus or minus 1? Yes, negative 1 to even power is plus 1, right? So, answer? 11 is a quadratic register. That's called Gauss Law. All right? We'll see why. At least understand the statement. Negative 1 to the mu, that was his theorem there. We counted the mu is 4, right? So plugging in the 4, it turns out it's 1. So this value is 1. So it's... But think about raising to the p minus 1 over 2 versus just doing the multiplication. If the computer does it, it's probably a lot faster calculation. Because all you have to do is just simply multiplying same number and reducing mod versus repeated square. But repeated square method is really fast, so it's quite comparable. So it is not really practical purpose. He uses lemma to come up with even something better one. But it is something available right out of this Euler's criterion. Right? So let's look at the idea. What was the idea? Yeah, half register system, if you multiply A in there and you see A copies of L, you see as you multiply all that thing, you have A to the L. And that's Euler's criterion, right? So if I multiply A times 2A all the way up to LA, you see A to the L, where L is P minus 1 over 2, and you see L factorial. Is that right? So you're going to do, I think I call that one B, A, and B in here. I hope you're familiar with this notation. This is a product notation. K is coming from A and multiply all that K. So the residue that lands in, within that first half register system, these are collected and multiplied. How about here? We use J and put it in there. And if you multiply that, these two things is not the same thing as this one, right? Because it came from half residue and then this came from the second half residue. But idea from the Wilson's theorem is that if you change that to P minus J, that's going to fall back into the half register system again, right? So if you have 11, what is the other one? 19 minus 11? So it's 8, right? It fall back in there. So if I multiply that, I will have half residue, part of it, and remaining part of it, whether it's overlap or not, is a good thing to do. Okay? But if I multiply all that, and that will be rather this one in here, right? Not the same one. So this one is equal to that because I didn't do anything about, this is all the same thing, right? Whether it's for before L or after L is organized a different way. It is still all same congruence class and A to L and all that. But if you want to change that to P minus J, then it looks like all half register system. But if I throw in one more negative one in there, they cancel each other. and became same thing as before. I hope you agree in that part. Mod p. Because negative cancel here, right? This is the same as negative j. So how many elements are in this B? That's precisely by definition Gauss lemma was mu, right? How many of them are outside that in there, right? Okay. So this will be, I'm just going to call it J tilde. It's back in the half register system. This one is here, half register system. And this, I'm going to call it B tilde, and we're getting J tilde out of it, and J tilde. Now this is already in half register system. This was outside half register system. I took the complementary part and bring it inside. As long as there's no overlap to this one, it'll make the full half register system, right? Does that make sense? Yes. Then they cancel out. This L factorial is a full half register system, and here everything is there. They cancel out, it giving you a to the L is negative 1 to the mu. Yeah. Let's think about it just a few more seconds. Make sense? This A here is from there, whatever in here that falls inside less than equal to L. These guys are outside L, but I changed that value to P minus J to make it inside, compensating with multiplying negative 1. But how many of them? There are mu of them, right? So I factored it out. There are mu copies of negative 1. These are now all within half register system. The question is that, will there be overlap? If there's no overlap, the count is perfect. It came from L of them. Some of them are outside, brought them back in. There's no repeat. There must be full L of them right there. Different order. Right? If A and B tilde intersects empty, right? Then this will be different order of multiplication and L factorial. Everything is there. And these two cancel. That make sense? Right. Why is A and B tilde is empty? Is A, all of them are coming from AS, right? If it is equal to that, some of them, it must be B, P minus J, J tilde. Think about it. This B tilde looks like this, J tilde. J tilde must be P minus AT, because J come from this shape in there. It's mod P. That should be true. Correct? If there's ever an overlap between these two things, AS came from the first set, this J tilde AT came from there, but we switched the sign, so these should two overlap. But if you solve that, P is just 0, so AS is congruent to negative AT, mod P, A is relatively prime, so they cancel, and it gives you S times S plus T equals 0 mod P. Right? What is still wrong with this one? S and T both varies. They came from this 1 through L, right? A times L, so S and T both less than 1 through L. What could happen to S plus T? Largest one, 2 times L, right? Smallest one would be, there's no 0, so it'd be 2. But what is L? It's P minus 1 over 2, correct? So it's all together P minus 1. So S plus T is in between 2 and P minus 1, and it has to be 0 mod P. That makes no sense, right? Therefore, there's no overlap. So if you can actually see that, let's overlap. 11 got 8, right? What is 14? 19 minus 4, is that 5? There's no overlap here, right? How about 17? 19 minus 17, that's 2. There's no overlap 2 here, right? 12, 19 minus 12, 7, right? There's no 7 overlap. So if you look at this larger one and flip the sign and change the sign, it all fill in the perfect half register system. So they become L factorial. So the statement after that is that a to the L is congruent to -1 mod mu, mod p. But what is h to the p minus 1, right? So that is um, Euler's theorem, that is equal to quadratic residue symbol. So because plus minus 1 mod p, either plus minus 1 is the same as equality there. And that's Gauss's theorem. All right? That's the idea. From Euler's theorem, we consider this half residue system, multiply all A, and product, that gives you A to the L. Same thing as Fermat's little theorem happens with more of -1 business taken care of. All right. There's Gauss' lemma. All right. Interesting idea that multiplying a product is so interesting. Here's the quadratic reciprocity again, and we'll prove it today. You can flip it. Residue property does not change if at least one of these prime factors 1 mod 4. If both are 3 mod 4, it changes quadratic residue property. And this special property, 2 mod p and -1, is called supplementary quadratic reciprocity law. Supplementary law of a quadratic reciprocity. Here's the proof. The book's proof is very elementary and readable, and I don't find me explaining that idea. You can read it, you will understand it. It was that elementary. But this is really fun. You see the big picture, and you actually see, if you look at the proof of like in the book, oh, I understand the proof, but you don't have an idea of why is it working like that. Yeah, like physicist point of view, you want to see the action, and here is that kind of proof. Field theory. We've been looking at the field, and I ask you to at once believe field extension exists, right? And we believed it. We play with the notation, square root 2. If you square it, become 2, things like that. So this is called field extension. That's something bigger than our finite field, using this like square root 2 and something like that. So we've seen that before, field theory. Next little thing is that what is different about this statement is that x to the m equals at most m solution. We've seen this one before, right? But what's different is not fp. It's k. And it's so powerful in here. X to the m has at most m solution in fp. No problem, right? But why is this still true? If k is a ginormous, if suppose it has billions of elements in this finite field, why does it still have m elements? No more. Doesn't matter how big your field gets, you're confined to this m solution. If you factor it, except m factors, that's it. Doesn't matter where you are, all the m factors, all you're going to get out of the polynomial. So you have no more than m solution. But this statement is so powerful, you will see. And this is the very property that make the field have a primitive root. Remember that part? Yeah. So that we can find some divisor that doesn't, and all that. It's interesting property. Now, using that, I'd like to throw this statement. You are in K. We created K using the square root of 2 and square root of 3 or square root of I. You have all the bunch of square root and third root of all mingled together. And they're added together, multiply, I give it to you. Is this inside FP? Who knows? It looks like complicated, maybe some algebraic properties, simplified, all that, get down to FP, right? So here's a question. If there's a massive expression, how do we recognize an element is inside FP? Even though it is expressed in K, right? Simple idea. The answer is the following. You take that element and raise the pth power. If you go back to the original element, that element must be in FP. And I want you to prove it, word by word. Let's prove it in the air. I'm not going to write down the proof. We're going to prove word by word. Why is that? Yeah, it's get bigger, right? Why not? Why not more elements satisfy that, right? If you're inside FP, of course that's satisfied. That's precisely the Fermat's little theorem. But if you go bigger, there could be more elements that satisfy that property, right? But it says no. Only element that satisfies x to the p minus x is that FP. Can you relate back to the first bullet item? How many elements can satisfy this equation? At most p. And how many do we have? P from FP, right? Therefore no more. It's that simple, right? It's that simple. If you know x is non-zero, then you can even go down to this more group theoretically plausible statement. X to the p minus 1 is 1. Simple as that. This is all we're going to use in the proof of quadratic reciprocity. So the fact that even though it's a field extension, it's still mod p world. So it's not in mod p, but we call it over fp. It's constructed over a finite field. But this exponent world is different, right? It's mod p minus 1. Those are two different modular world. Does the reciprocity? That was the key, yes. Right, if root 2 is a quadratic register, 2 is a quadratic register, if so. If not, it switches the sign. Yeah, it switches the sign. Yeah. But we do use that from freshman stream, right? Now you know what we mean by freshman stream, so I'm going to give you a more sophisticated name for that, right? It's just still, now you ditch the freshman stream. There's somebody mentions that, oh, that is called this, not freshman stream. That's the right name for mathematical. That name is Frobenius automorphism. Again, this is a fancy term. All you have to know today is just this one item right here. If x to the p is x, you know it's f inside fp. That's all we care. But algebraists make a big deal out of it. What just happened in here is the following. The left-hand side action, I give you x, you raise the pth power. That action is called Frobenius action. It happened as an automorphism because of the freshman stream. Think about it here like this. X plus y. Raising the pth power is a map, it's an action, right? But you know it is like additive homomorphism because of the freshman stream, right? Because of that, it's a field automorphism. That's why it's called automorphism. So this one has a special name, Frobenius automorphism. So freshman stream, what is the fancy name? Actually, Frobenius automorphism is a good name for that. Yeah. Yeah. And here, x to the p equals x. That one is now described here as like this. Sigma of x, that's a Frobenius automorphism. You do something, and it's get back to itself, right? It didn't change. This action does nothing to that fp. In Gauss, the field theory is called fixed field. Automorphism will move things around. But FP here is precisely not moving. That's precisely element is untouched by this action. So FP is precisely the fixed field. And this relationship is called Gauss. However complicated your approach using algebraically, using polynomial, and splitting field, and normal, separable extension, all that boils down to this amazing property, fixed field being that bottom field. So I describe it like this with the picture. It's just additional explanation to our proof. For our proof, all you need is just that second bullet item. I got this. That's the picture right here. Frobenius automorphism was a sprinkled donut with but what I meant to say is that if you hit this one with a Frobenius automorphism, it goes there, swirling. Everything is moving around. Frobenius automorphism will move things around. Nothing is fixed. Yeah, it's like that. These guys all move. It's like storm. But inside, that's FP, right? The Frobenius automorphism does nothing to that FP. This guy is just staying there. It's not moving to something else. But automorphism move things around. Inside FP, eye of the storm. It's like nothing happens. Quiet. That's FP. That's the Frobenius action. All right? Okay. So here's the first magic coming to you. All right. Now, I use I square root of -1. It's a fun notation and has this amazing property. Doesn't matter where you are, what kind of prime you are, this one has order 4. This universal property has nothing to do with the P, is what we're utilizing. If I created this field, it could be FP itself. That's the whole thing that you have to consider. We created this I and play with the FP, but this -1 could be quadratic residue mod P, right? In that case, all we are doing is everything is happening FP. If it is not in FP, then it's really truly bigger field, right? All right. Is this I inside FP? That's the ultimate question, right? Is the square root of -1 back in FP? What did you learn today? How do you recognize something is inside FP? How do you recognize it? Frobenius, right? You hit it with a Frobenius like that, and it should be back into itself. If and only if I is inside FP. Quadratic residue of -1 or not is this property right there. Isn't that right? Yeah. So if you go back to the group theoretic statement, is this one, right? So what's the order of P minus 1? I mean, order of I? Order of I is 4, right? So yeah, remember that some A to the L equals congruent mod P. If the order of A is K, something divides something, right? Yeah. Order of I divides P minus 1, thank you. What is order of I? 4. P minus 1 divisible by 4. That gives you P equals 1 mod 4. This is the coolest proof. Don't you think? Just think on top of that exponent world, it gives you the answer. All right? If P is congruent 1 mod 4, and this one divides and go back and does all that. Okay? So by just looking at the larger field and exponent world, you conquer that statement. First, we learned through Wilson's theorem, and second, we learned from Euler's criterion, and here's a different description. All right? Next level is 2, and they thought about how to play with this one. So I wrote it down there. Yes. No. Let me summarize it here. The statement is this. Is I inside FP, that means is a -1, a quadratic residue, not Q star, quadratic residue P. If -1 is a quadratic residue, square root of -1 is back in our FP. So that's the statement. That's the equivalent statement. Right. So that's what we're deciding. And if you look at this Frobenius action, raise to pth power, we want this back to is I again, right? So that's the equivalent statement, which is all perfectly proved, but still amusing. And if it is, the idea is really interesting. If you raise the pth power back to itself, you've proven it's back in the FP. So we looked at the statement, come up with divisibility, right? It's very, very cool. All right. So they play with the 2 and other numbers. They found the 2 and I quite related. Remember 1 plus I squared is 1 squared, right? 2I plus I squared, right? Special about I squared in here, they cancel, correct? So here's a 2I. So if you raise s to the second power And to get the 2 out of it, if you multiply negative I and you have a 2, you can pull out 2 out of it. That's the statement there. They have. It is a very special situation, but they generalize it nicely later with that one. They want to turn this 2 as a square. Already I have a nice square right there. It's 1 plus I squared. So they wanted to put this I and negative 1 inside. Negative 1 is good. Negative 1 is square of I in there, right? I squared is negative 1. So his I is out there. 1 plus I squared. So that's a square. That's a square. We're about to witness how the square root 2 looks like. But I is not a square, right? I is not a square. So they wanted to make I square, you have to go bigger. And this is order 4, right? If you want a square, it becomes order 8. So that's the trick. Bring in order 8. Let there be an order 8 element in our world. Then I can write I as a square of the zeta squared. That's the. You can always bring this convenient element that has this property in the bigger field extension. Yeah, just believe it exists. Order 8. Then this happens. This is all happening in complex numbers actually. But we actually do everything that is happening in complex number algebraically within finite field. This 8th root of unity in the unit circle in complex number, for example. All right, then what happens is that 2 is there. Now I squared, and that's a zeta squared I. It's 1 plus I squared, right? Everything is squared. So you can put it inside. I zeta and 1 plus I squared. Because of that, I can write square root of 2 is inside this element, right? Yeah, I times zeta 1 plus I. Whether it's going to be plus or minus is not very important. Whatever you choose, remaining will follow depending on that choice. Now I can rewrite this I as a zeta squared. So here is idea 2 square root of 2 is a zeta squared is zeta to the third, right? 1 plus zeta squared in there. So if you expand it, this is the third and zeta to the fifth. If you have noticed that there's an 8th root of some element in order 8 in field, and if you third power and plus fifth power, and it's automatically square root of 2. This is like a universal statement. It doesn't depend on your choice of P or anything. And now you bring it in P, and the property kicks in. Order 8, yeah. Order 8 that makes this I into a square root. And then this is a square, and that's a square, and that's a square. So I have expression of a square root. That's right. Yeah. Keep making it bigger so that you see the square root in it. If you don't see the square root, make it even bigger so that you can have some sort of expression of a square root. Is that okay? Next question is that, is this inside FP or not, right? That's an example. Oh, that's an order 8 and added together. I don't know whether it's inside FP or not, right? But what is the method? Frobenius action. You raise this one to pth power and see if it is back into the shape. For example, if I raise that to the pth power, right? By freshman stream, this one, or because it's called Frobenius Automorphism, it distributes like this, 3p plus 5p, right? Okay. How is this exponent world? Is modulo what world is it? Not p minus 1. No. It's the order of zeta. What is the order of zeta? 8. So it's a mod 8 world up there. Mod 8 world. Remember 2 quadratic residue, mod 8, that supplementary quadratic reciprocity is coming from this relation. All right. So where is square root of 2? Square root of 2 right here, right? How on earth can these two be equal to each other? Maybe 3 and 3p are equal to each other, right? That never happens with a prime number, but it may happen modulo 8. Then it's going to be 3, 3. That's the same element, right? How about here? Consistent. Isn't that right? Mod 8. So conclusion, if p is 1 mod 8, this is going to be equal, that's going to be equal. Therefore, after you raise the pth power, you are looking at the same statement. Therefore, it's fixed. Fixed field, right? So square root 2 is in where? Fp. P is 1 mod 8. If P is 1 mod 8, this is the same as 3 mod 8, the same as 5 mod 8. So therefore, it's exactly the same as before, right? But it's possible it's a cross like this. 5p is 3, congruent to mod 3. 3p is congruent to mod 5, right? Yeah. Can you go ahead and solve that? Can you go ahead and solve that just for a little break out of just listening to me? So you got the 1 mod 8. Let's try this one here. See if that's consistent. And 5 is 3 mod p. What do you get out of that? You solve one equation. It's not Chinese remainder theorem, and it has to be consistent with the second one. Can I have your answer? What is it? No, 3. If you put 1 in there, 3 is not congruent to 5 mod 8. We're doing this alone. This 2. Yeah. If it is 1, is 3 is congruent to 5 mod 8. That's not true. Yeah, I see how you got that one, but you don't have to square it. You can just solve this one by multiplying multiplicative inverse of 5. Yeah. So you overdid it. Yeah, yeah, yeah. All right. Right, right. So answer? Multiplicative inverse of 5. Let's do that. Multiplicative inverse of 5. Are you claiming 5 is multiplicative inverse of 5 itself? Okay, I accept that. 5 and 5, so multiply that. What do you get? 15, which is 7, right? 7. Right. Yeah. But if you go back, supplementary alert, that's it. 1 and negative 1. It's 1, 2. Yeah. Yes. So it's consistent. The question is that, all right, by matching this one like that, we got 2 solutions, right? Isn't it possible that different, because it's just an expression. Think about all the trigonometric expressions. They're totally different, but they're equal expression, right? So we have to think about it like that. But it turns out algebraically, if you look at all the powers, some of the distinct powers less than 8 is a unique expression. It's some algebraic fact about anything that has in the field with order 8. So this is it. That's the only way that these two can be the same. 3, 5 and 5, 3. That's it. So that gives you the solution. All right. So what's happening again? Downstairs is mod P world, right? What's upstairs? Mod 8 world. That's how this one is interacting. As we do the Frobenius, put P in the upstairs, right? That's right. 2 is congruent to quadratic residue 1 if and only if it is either P is 1 mod 8, 7 mod 8, right? It's part of the quadratic reciprocity. Fair enough? hmm 1 mod 4. Mhm. But that does not require, it is about, we use this algebraic fact, but it doesn't require P is 1 mod 4 not. Right. Whether I is inside FP or not, that is not required in here. Like you said, if I is inside FP, good. If not, there's one field extension. And then as you go throw in 8, again, the even bigger field extension. So these, yeah, that's right. These facts are nothing to do with the P. That's a universal statement. Yeah. All right. When you push to 7, it gets really interesting. Yeah, all sorts of things that kicks in. What are you looking at? Geometric series, right? Geometric series. Anybody remember the formula of geometric series? They thought about how to utilize what is just observed, and they came up with this neat trick. And beginning is weird, but you'll like it probably. So anybody remember the formula? Have taken exit exam yet? Got to know this. Right, it's a common ratio minus 1, right? And x to the number of terms. How many terms are you here if it is perfect geometric ratio? 7. Counting this one is a 7. 7 minus 1. That's it. R to the number of terms minus 1, common ratio minus. That's a geometric series, right? Fair enough? Now, they turn this one into very, very algebraic statement and give a fancy name to this one. It's called cyclotomic polynomial. That's a fancy name. The left-hand side of this one is called cyclotomic polynomial. All right. Look at here. All the x to the 6 is equal to x to the 7 minus 1. That's good. Rearrange the statement you already know, geometric series. Now you're looking at zeros. What are you looking at here? If it is a 0, what kind of elements are you looking at here? Primitive root of order 7. Any element, zeta, whose order is 7. We're looking at order 7 elements, right? Where is it? It's somewhere out there. Just invite and make it into a field extension K. Now K has zeta in it. Because the order 7, you know this has raised to 7 power is 1. That's raised to 7 power is 1. That's raised to 7 power is 1. All the way up to zeta to the 6th, right? If you raise that one, it's still 1. So these are all zeros of that, right? So how many of them are here? 6 of them. How do you know they're all distinct? That's the very definition of order, right? They're all distinct. And x equals 1 is one of the thing that makes this one equal to 0, right? So if I cancel that, and this polynomial has at most how many zeros? 6 zeros. And I'm looking at all the 6 elements that is not equal to 1, right? Therefore, I claim, because of the counting has amazing consequences sometimes. This cyclotomic polynomial is factored into x minus 1 of the 0, x minus second 0, x minus third 0, x minus fourth 0, x minus fifth 0, x minus sixth 0. Do you believe that? I have just argued that these are all the zeros of this polynomial, right? It should be all appearing here if there's not one. If there's no other possibility. I don't know what you're doing. No, it's a 1 plus 2 plus 6. Yeah, it's addition this time. Yeah. Right. Actually, doing this algebra is a lot of work. And even Gauss studied this one and called this is called cyclotomy. That whole area that he was doing back then was called that. But this the statement, yes. Mm. No square root of the Taylor series because this has infinite nature, and right now it has no room in a finite field because there's no infinite sum in the finite field. There's long time goal in mathematicians how to bring in naturally the geometry we use into the finite field. That has been ultimate goal of an algebraist, and that will be the eureka moment. People haven't done that yet, but some successes there, like Riemann. Some of the rudimentary level of topology was realized inside the finite field using cohomology theory and things like that. But the full geometry is still not there. People are doing crazy things to make that happen. But some of the things work, which is very algebraic like this. But like that kind of thing is still not there. Yeah, yeah. But it is good to think about it. Just you know, with an ambition, I'm going to just do the same thing we're doing. And if there's an obstacle, you're going to try to fiddle and fix it. And but people have been doing that a lot with the finite field. Try to make it what would the tool so that all the geometry come in back in there. But right now is that. And amazing thing pull out is that as you plug in x equals 1 in there, what do you see in the left-hand side? 1, 1, 1, 1, 1, 1. 7. That's how they bring 7 into that, right? Out of all that, by plugging in 1, and then you pull out 7 in there. Now you have 1 minus zeta, 1 minus zeta squared, 1 minus zeta to the third, 1 minus zeta to the fourth, 1 minus zeta to the fifth, 1 minus zeta to the sixth, right? Your goal is that you reshuffle this one and pull a square out of it, just like Wilson theorems did. What did Wilson theorem did is that what is the mod 8 level is the exponent, right? Mod 8 level. So you can play with this negative 4 instead of that. You can play with a negative 3, algebraically manipulate because it's, you know, same thing, right? 5 is congruent to negative 3 mod 8. 6 is congruent to um, negative 2 mod 8. Things like that. It's not 8, I'm sorry, it's mod 7, right? Because we now enter mod 7. So that's mod 3, mod 2, that's mod 1, right? Then we have this overlap in 3 and 2, 1 and in there. Maybe that's going to create the square root, and that's their idea. So I'm going to show you how they pull out an overlap. They first factor out zeta to the fourth out of that. And then you have 1 minus, here's a zeta to the fourth there, right? Negative fourth. Good. Minus 1. Is that right? But what is negative 4 mod 7? Yeah, zeta to the 3. That looks exactly like that. 1 minus zeta to the 3. Except negative 1, right? Good. So here's the negative 1. Zeta to the fourth. 1 minus zeta to the third. Make sense? So I can change each of them like that. And I like to claim that 7, and I have 1 minus zeta, 1 minus zeta squared, 1 minus zeta to the third. All of them will look like that. Negative 1 and zeta to the fourth, and 1 minus zeta to the third. This one will be 1 minus zeta squared. This one will be 1 minus e to the first. So I hope you see there's exactly 2 of them coming in. And then negative 1 to the what power? How many negative ones are there? 1, 2, 3, right? That's the number of half register size. 7 minus 1 over 2. That L minus 2 in here. So that's 3, right? And there's a bunch of zeta to the b. Whatever that piles up. 4 and 5 and 6. So this negative ones move over there. And because it's a 7, this is always, in mod 7, is always can be rewritten as 2 times b prime because 2 is congruent relative to the prime to 7. So this guy turns out to be always a square. So we can go inside. I'm going to use b0, 1 minus zeta, 1 minus zeta squared, 1 minus zeta the third, all things squared. Now they finally pull out square root of something, but it's negative instead. That's what is available. But we can handle negative using 1 mod 4, right? 1 mod 4 technique. So that's zeta to be 0, 1 minus zeta, 1 minus zeta squared, 1 minus zeta is the third. Here, they come up with using 7th root of unity, 7th order of elements of order 7, they were able to describe square root of negative 7 explicitly like this. Our question is that when is this guy inside our small field FP, right? This is all happening in big K, where we were playing with this 7th root of element of order 7, whether it's inside or not, we have to use that. So how do you know if it is inside there or not? Frobenius, right? Then it goes into there. So PB0, pth power, negative 1 z to the 2 times p, negative 1 z to the 3 times p. This was a half register system. Is that right? And I multiplied p through it, but it's up there in the mod 7 world right now. All is happening in mod 7 world, right? Exponent. And here's a half register system of mod 7. I multiply p throughout. And some of them will come back into half register system, right? Some of them will go outside. Remember that part? And then how did we put them together? So some of them will come back, and those who go outside half the register system, we have to subtract from p 7 minus p, and then bring it back to here like that. In that process, you have to do this business again. But how many of them are falling outside? If you do every time when you do that, when you're switching, you're the negative 1 kicking in, right? Every time when you're going outside, when you switch it back into that shape, we have to throw in negative 1. And how many of them are? The notation was negative 1 times mu. That's the Gauss lemma thing, right? How many of them are falling outside? So emphasizing that it's in the mod 7 worlds, I'm just going to call mu 7. It's a mod 7 world. And then there's another bunch of zeta to the something is there. I'm going to call it C. So all together, pile them up here, we have zeta to the D. I'm going to call it. It looks like that. If you raise the 7th power, the pth power, this one is reshuffled perfectly nicely using the Gauss lemma into the original shape again with a bunch of copies of negative 1. So we want to see if these two things are equal to each other or not, right? If these two are equal, then square root of negative 7 is inside FP. If it is not equal, it's outside FP, right? So if you divide this one, it's clear that these two things cancel. If you divide that, you have a p minus 1, right? Divide each other. And we have this one and that one perfectly cancel because that's exactly the same thing. And there is this some junk here, and there's negative 1 to the mu 7. The final trick is coming in here. This is same as 1/2 power, so you can write it as a negative 7 p minus 1 over 2. I hope that's okay. Right? It is true. N equals and zeta to the whatever power, -1 to the mu 7. This one, we know this is either plus or minus 1, right? And because this has odd order, this will never be equal to -1. It never happens. If it is -1, it forces this one to have an even order. So this actually never happens with -1. So only possibility this can have plus or minus is +1. So if you actually calculate it, the exponent magically just cancel and giving you the perfect multiple of the order 7. So it always arrive to that point. So according to Euler's criterion, what is this one? Is a -7 mod, this quadratic residue, whether -7 is a quadratic residue or not, right? Right-hand side is a -1 mu 7, right? What is the mu 7? It's a mod 7 world. This is mod 7. Where we play with the multiplying through p. So whether p is a quadratic residue mod 7 or not. If you look at this world in a mod 7, that's what that is. Mod 7, a is a quadratic residue or not. Mod 7 is multiply that a and how many copies is going outside the half residue system, and that's this a in here. But these two are equal to each other, -1, congruence and whatever, and they're same. And that's the reciprocity just happened. -7 over there and p over there. Okay? Doesn't matter. This -1 it will take care of it. If p is 1 mod 4, then is the opposite. Let's see. Is that correct? Yeah, I think it still works. Yes. If it's yeah, -1 there, -1 p and 7p is a p over 7. So if you want to take the reciprocal of that one, you need to know whether p is 1 mod 4 or not, right? Like the homework problem. If p is 1 mod 4, then you can flip it, right? P is 1 mod 4, this is 1, right? Because of that, p is not 1 mod 4, then you have to assume one of these is 1 mod 4. You flip it and it just takes care of it. So it checks out, yeah. But it's worth checking, yes. All right, because we're running out of time, it goes exactly like that, but it starts like this 1 x plus x squared plus all the way up to x to the q minus 1. That was 7. It was a 6 like that. And then this factors x minus zeta, where the zeta has order q. Go exactly all the way up to x minus zeta q minus 1. Then -1 times L, which is q minus 1 over 2, half residue system of this one, to the L times the q square root 2 is described in this form, all the way up to half residue system. By flipping over, everything works out nicely. And negative piles up here, it's over there. And you raise that to the pth power and compare with that one. Again, the Gauss lemma gives you exact overlap. So pth power is again another stuff in here, and -1 mu q, an exact copy of that. I mean, if you think about that, what happened in the mod 7 calculation, it was quite general. So I'd like to claim that it works exactly like that. Question? Right, right. Because before you put in the pile in the square, you have to move the negative over there because we don't know if it's squared or not. So they deal with just this part. So if it's squared, if you divide it and you have L, I forgot the L, P minus 1 over 2, and they all perfectly cancel out. And this again, because it's odd order, giving you only possibility of the mu q. Mu q is again, P is multiplied throughout in here as we do the Frobenius action. So this is equal to whether P is a quadratic mod P mod Q. And this one is by Euler's theorem, -1 to the L Q mod P. They're equal to that. Now if you separate that -1, Q minus 1 over 2, P there, right, is equal to Q over P is equal to P over Q. But what is this one? -1. It's 1 or -1, depending on 1 mod 4, -1 mod 4. By Euler's criterion, back in this one again, -1 to the P minus 1 over 2. Out there is a Q minus 1 over 2 times Q over P is equal to P over Q. So if any of these things is 1 mod 4, that's going to be even number. Both of them are 3 mod 4, that remains odd number. That is quadratic reciprocity that you've seen. We're able to flip-flop. Perfect timing. Field theory. Field theory. Go to, cyclotomic world and play with this algebraic property, being able to pull out what's happening down there, FP and FQ. Wonderful theory. And they use this framework to generalize cubic reciprocity and quartic reciprocity and quintic reciprocity, mth power reciprocity. Finally, that I think people spent pretty close to